I know the organisational people here and myself chairing this are absolutely delighted that Dr. Sue Bowler has stepped into the breach at very last minute to talk not about gravity waves, but about 50 years of plate tectonics. Thank you, Sue.
Well, first of all, I'm very pleased and not a little surprised to be here. But I want to talk to you about a project that I've been involved in with the Geological Society, and it's about plate tectonics. Now, we know plate tectonics. Here's a map colour-coded for the age of the ocean floor. It's very young where it's red, very old where it's purple. This is the idea that ocean floor forms at the mid-ocean ridges, spreads, carries continents with it, or subducts under the continents. Now, these anniversaries, these 50 years, they're quite often quite contrived. This is no exception. We are actually celebrating just about the publication of this paper, Mackenzie and Parker, 1967. We're in the right month. This is good. And this was the first paper that set out the kinematics of plate tectonics, how the plates move, right? The authors tried really hard. It doesn't actually mention plate tectonics. It talks about plates, it talks about tectonics. They tried really hard to call it the paving stone theory of world tectonics, but it didn't work. Why are we celebrating it? Well, one of the authors of that paper, Dan Mackenzie, who is a fellow of the RAS and of the Geological Society, has very generously donated his archive to the Geological Society. All of it. Scribbles on bits of papers, letters, everything. It's an absolute goldmine. Librarian Fabienne Michaud and archivist Caroline Lamb at the JOLSOC have put it all online, basically. You can go and root through it and read original letters and articles. And it's accompanied by a truly excellent website telling the story for a wider popular audience. Now, I say that's an excellent website, and that's because I wrote it. So I would really strongly encourage you to go and have a look, see what's there, explore, find out. Because your judgment may be, for some reason, different to mine on this. So, 50 years ago, it was the summer of love. People were apparently doing all sorts of strange things in funny-coloured buses. But this is when plate tectonics took over, basically. It's very hard, thinking back, to know how people thought about the Earth before this. But it's not the first time people were thinking about the continents moving around the surface of the Earth and changing their arrangements. This is Alfred Wegener, who has, I should point out, a very fetching hat. I'm quite taken with that. Now, Wegener was 1880 to 1930. He was a polar scientist, and he was utterly seduced, as people before him and after him have been, by the apparent fit between the east coast of South America and the west coast of Africa. And he realised that if you sort of squished the continents together, an awful lot of things matched up. Fossil assemblages matched up. They were the same, Australia, South Africa, South America. You could get rocks that formed in the same way, desert rocks that are now up at high latitudes. Oh, you know, they match up. They must have formed in the tropics. He was such an enthusiast for this idea that, as well as the good and things that we can see now did make sense, he just pulled in any old evidence, however bad, to support his ideas, particularly some very dodgy geodesy and a particularly dodgy mechanism that a great RAS fellow and supporter, Sir Harold Jeffries, really took apart. I mean, Wegener actually suggested that the continents moved by ploughing their way through the solid lava, volcanic rocks of the ocean floor. And Harold Jeffries pointed out that this was nonsense, you know, just wouldn't happen. And basically, continental drift wasn't really taken seriously for the middle decades of the 20th century. And one of the problems, though, because it's very tempting, you want to believe it, but the evidence, of course, is not necessarily on the continents, it's in the oceans. They're 2/3 of the Earth's surface, and if you want to know what was happening, you'd really need to look there. The problem with that, of course, is that for most of the 19th century and quite a bit of the 20th, this was the general picture of the oceans. They were really fairly mysterious, and it was quite likely that a squid would come and get you. I mean, all we knew about the oceans came from a wonderful expedition, the Challenger expedition, in the 1870s, where a little Royal Navy corvette was converted. It was 200 feet long, 40 feet wide, and it carried, on this voyage to travel the world's oceans, amongst many other things, 181 miles of hemp rope. And basically, it sailed around and dropped the rope over the side to see how far down it went. And they found some surprises. They found amazingly deep areas quite close to land, and they found surprisingly shallow areas in the middle of the ocean. Some of the rope they dropped down, they made soundings, had balls of wax on the end, so they hauled up bits of sand, bits of volcanic rock, which was quite helpful. The other source of information was the telegraph companies, because they sent cable-laying ships in the second half of the 19th century across the Atlantic, and they too found hills where they weren't expecting any. But it took warfare in the 20th century, and particularly submarine warfare, to make a difference. In the 39-45 war, this was the first one where submarines were a threat and an opportunity, depending on which side you were on. If you haven't seen this wonderful drama, Das Boot, set on a German U-boat, I do recommend it. It involves a lot of very silent running, because one of the tools of submarine warfare was sonar, sound waves under the sea, either passively listening for sounds of the engines or people dropping a spanner. That's a particularly tense moment in Das Boot. But that evolved into sending out sonar beams, because if you want to know where a submarine is, you've got to know what shape the seafloor is around it and under it. So that produced development during the Second World War and afterwards. But the Cold War really refined that, because there was an awful lot of hunting and hiding with submarines after the 39-45 war. And magnetometers that could be towed behind ships at sea were developed to actually start looking for the perturbations to the magnetic field from submarines. And that, of course, meant, again, you had to map any magnetism held on the seafloor. So this was all going on. It wasn't entirely a military effort. The big American geophysical institutes, Lamont Doherty particularly, but Scripps as well, had fleets of ships. Lamont had 5 research vessels at sea for quite long periods. And this produced maps. You can just about see South America here. You can see Africa. This is Bruce Heasant, Marie Tharp. They made the first world maps of the ocean floor. And you can see they're actually helpfully pointing at this chain of mountains up the middle of the oceans. This is the mid-Atlantic ridge. They were found on all oceans, which was interesting, and that got people thinking. This map is coloured for depth and topography. In 1961, Harry Hess, who had served in the US Navy during World War II, he finished as an admiral, he saw a lot of classified information, which actually helped. But he suggested that these mountain chains, which were also a little bit hotter, they had a bit of a higher heat flow than the surrounding rocks, they were thought to be volcanic, they were where the ocean floor was made, and it cooled and moved each side. This was called seafloor spreading, and nobody really took very much notice of it. You know, nice idea, but come on, prove it. A young research student at Cambridge, Fred Vine, and his supervisor, Drum Matthews, thought they could prove it using some very new data that came from land. And this was measurements of magnetism trapped in lava, piled up one lava flow after another for millions of years. And as the lava cools, it traps in the minerals, it traps the orientation of the magnetic field at the time. And people who were doing this work found that the magnetic field had changed direction, it had reversed. So Vine and Matthews measured the remnant magnetism in the lava of the sea floor and found what they said was a symmetrical pattern about the ridge. Now, it's not very good data. And again, this didn't really make very much of an impression because nobody really thought seafloor spreading was very much. And this magnetic reversal, that was a bit strange as well. You know, who thought that could happen? That was in 1963, Vine and Matthews published. There was also a big problem at this stage with data quality. If you're navigating in the North Atlantic and you're not doing it by any form of satellite, you're doing it with a sextant and dead reckoning, you're not always very sure where you are. The next step in the story came in 1965. This is a paper from a diagram from a paper by Bullard, Teddy Bullard, Everett and Smith. And what they've done here is put the continents back together again. But they've done it, crucially, with no reference at all to continental drift. They've done it with a computer. This was cutting-edge science. The computer was probably the size of this room, but they managed to do this. And they did it particularly using very simple spherical geometry, using the fact that you can move any two shapes round on a sphere using just simple rotation about a pole of your choice. And this was really done almost to distance any of this new idea from all that continental drift nonsense that nobody believes. So that's pretty much where we are. Round about, this is a picture of Dan Mackenzie in some stream in Scotland when he was an undergraduate. We're not entirely sure where. So 1965, Dan was a postgrad student. He had started his PhD in 1963 on the viscosity of the mantle. And some work he did on that in the second year of his PhD won him a research fellowship from King's College, Cambridge. That basically meant he could do what he liked. So he went to America and went to the various big geophysical institutions to find out what was going on. Because he was Bullard's research student, people visited the department at Cambridge. He knew what was happening here, and he went to find out more about it. And one of the sources of data he found out about was seismology. Now, this is war again. After the first nuclear bomb was dropped in 1945, the first two, there was a certain amount of concern politically of how would we know if other people were testing bombs? And of course, you can tell with the seismic waves that they produce. But at the time, 1945, you couldn't really. There wasn't a coherent, organised network. So that network was put in place. That was considerably helped by International Geophysical Year. But this network was put in place, and the instruments, the individual instruments, were calibrated so that they would record consistently whether it was a compression that came first in the wave or a rarefaction. And of course, if it's all compressions first, you have a bomb. If it's movement on a fault, you get a different pattern that in fact tells you how that fault was moving. You get a slip vector. That's very interesting. What it did first was pin down immediately the locations of the earthquakes. This is a modern plot. I couldn't find any of the sort of really early plots of global earthquake locations, but they didn't look like this. This was the first time people could see that there are pretty much no earthquakes in the middle of the oceans. They're all round the edge, which is quite important. Now, Dan Mackenzie looked at this and saw that what this meant was that these vast areas, these vast plates, are essentially rigid. And the movement, if there is movement, is going to be around the edges, and it's going to be shown by the slip vectors of those earthquakes. And happily, there was at the time a scientist and priest in the Midwest called Father William Stauder. He was actually tracking the slip vectors for the earthquakes around here. So this was what got Dan thinking, that you could track how this whole rigid plate here is moving. And he realised you could. He also realised that he was not alone in thinking this and working on this. At this time, he moved from Scripps on the west coast to Lamont, and heard that Jason Morgan, a much more established scientist at Princeton, was also working on this. He asked his boss what to do, and his boss said, publish. So he scuttled back to Scripps, where he was working with Bob Parker. Bob Parker happened to have a map plotting program called Hypermap, ideal for this. And this is one of the figures from the paper that they published in 1967. And these are the slip vectors. Now, he too, after Bullard's paper, he used Euler's theorem to describe this. And essentially, these slip vectors are going to be tangential to small circles about a pole of rotation, I don't know, somewhere up here. They are all the slip directions. This has got north at the top, so we're looking at California, that's Baja California. And look, there where we all know the San Andreas fault is now, the slip vector is parallel to the plate boundary, so it's a sliding fault. Much flurry of work, excitement, posted off to Nature, didn't hear a thing. In the interim, though, this is about October 1967, in the interim, he discovered that Morgan really had been working on this and was planning to publish. So he wrote off to Nature, to the editor, and said, look, is there any way you can do this? Can you delay publication until Morgan's paper in JGR and they come out at the same week? The editor of Nature at the time was John Maddox, who was famous for never missing a scientific scoop. And he certainly wasn't going to miss this one. So he wrote back and said, no chance. You know, it's coming out on the 30th of December. And this is the carbon of the letter Dan had sent, which he ripped up and chucked in the bin. And then later he got it out and stuck it together again. And the rest, as we say, is history. So let's hear from Dan.
I went from being an unknown graduate student, well, postdoc, to somebody who was one of the people everybody invited to a conference and paid their way, right? And it happened within a year. It opened up a whole lot of things to do, and I reckoned, you know, I had support at King's when I was in Cambridge, right? I had no commitments. I was not on the staff. I didn't have to do anything. Right, and so I reckon scientists don't get this sort of opportunity more than once in their life, and that I should really work hard and get on with it and see how far this all went. And so I was too busy to be conceited or anything. I just absolutely went hell for leather at this because, you know, I knew it was going to be competitive. By essentially 1968, the basic story was accepted, right? The people involved went from, I mean, if they were young like me, they went from being just, you know, a first-year postdoc to being central people in the field. Even the people like Harry Hess and Tuzo, who were well known before this, I mean, it was an absolute sensation that it all worked like this, right? And it was wonderful, you know, to be on the crest of a wave like that. John and I set about the Indian Ocean because nobody else had done anything with that. And it's more or less antipodal to the major US enterprises. So the amount of data there, right, was less. There was probably enough, if we did a solid job, to actually see what was going on. And we did that. We started in 1968. And the paper was published in 1971, 4 or 5 years later. I discovered I was elected to the Royal Society because of that paper, right, which had so impressed the Section Committee 5 that, you know, people could work out the entire history of an ocean basin, right, and get it right, right. Well, you know, in this way, and they were so impressed by this that they elected both of us to the Royal Society, not because of plate tectonics, which really annoyed me. Because I thought, you know, this was just really turning the handle, right, which is what it was. And we learned almost nothing new from that. Right? Everything worked. And that was really frustrating to me. I then really stopped working on marine geology and geophysics because I thought, gosh, we're done.
So, what did Dan do next? What did everybody do next? Well, you can imagine the flurry, the power of this technique, and people went out, it made sense of a lot of geological history. But Dan, of course, being Dan, headed off to the place that it didn't work. He carried on with an awful lot of modelling and all sorts. But the places that it doesn't work, you can see quite clearly, are the continents, and especially continental collision zones. And I want to give you an example of how fundamental research on plate tectonics actually gave us something of tremendous commercial value. And then finish with a little bit of speculation. So Dan moved into Iran for a while that was a good place to work, and then moved on to the Aegean. And in doing so, he solved a problem for the hydrocarbons industry. So at this time, in the 70s, North Sea oil's been discovered. They're finding lots of North Sea oil. Trouble is, they have no idea why it's there. The North Sea is on continental crust, and it has accumulated in the middle about 5 kilometres thickness of sediments. And they're all shallow water sediments, right? So it's been sitting there, getting deeper, filling up for no good reason. And of course, you can't predict, you can't go anywhere, you can't do anything if you don't know what you're doing. Now, this goes back to some work Dan did in 1966 between submitting his thesis and being examined. This was a time when people saw mid-ocean ridges and thought, that must be part of a convection system in the mantle. It's hot material coming up, great sheet, and then, you know, the plates make the top of a big convection cell. Doesn't work for a lot of reasons, but they could not make it work with the heat flow data. Dan had a different idea. Dan saw them as ice flows. He saw them as the plates moving apart, hot material welling up, and no reason for the mantle under the mid-ocean ridges to be much hotter than anywhere else. They were detached, they were separate. His model worked. So, here we are in Greece. Fundamental research on how the continents deform. And how the continents deform in the Aegean is great big faults. Here are some people. Here's a good 50-metre fault scarp. It's extending. Dan applied a variant, a very simple variant of that same model to say, what if you just extend the lithosphere and look at the thermal consequences? That's what he did in this paper in 1978, some remarks on the development of sedimentary basins. You start with the crust and lithosphere, you make it a lot thinner. The asthenosphere, the fluid hot material up, rises underneath, and then cools and sinks. Very simple, straightforward model. It gives you exactly what you see in the North Sea. This is a seismic section, this is the interpretation. Huge vertical exaggeration. The faults aren't this steep, but you've got all these faults first, followed by thermal subsidence afterwards. This was leapt upon by oil companies. It was exactly what they wanted to know. It gave them predictive power. And some work Dan did about a year later with an organic geochemist meant that you could use this pattern to predict whether or not the source rock would be buried deep enough and for long enough to produce oil and gas. So they had a predictive tool to know if they had a basin, is it going to have oil in? And all that came out of pure blue skies fundamental research, which is good. The other thing I'd like to think about, and this is what I'd like to leave you with as a bit of speculation, really. Earth is a volcanic planet, all right? We have volcanoes emitting carbon dioxide all the time. Plate tectonics is part of a process that returns some of that carbon dioxide to the mantle. And in doing so, it acts as a feedback. This silicate weathering mechanism is a sort of thermostat on our planet's temperature. If the temperature goes up, it works a bit more efficiently and cools it down, on a long-term geological timescale, of course. Now, there's a lot of volcanic planets. These are roughly to scale, Venus, Mars, and one of the TRAPPIST-1 planets, exoplanets, I forget which, but it's sort of Earth-like and a bit icy. You seem to need to have some sort of return mechanism. Otherwise, the atmosphere becomes very, very rich in carbon dioxide. Venus hasn't got one now. Mars hasn't got one now. Venus possibly had a very early, wet greenhouse, although it's lost a lot of its atmosphere since. The question I'd like to pose is, how important is plate tectonics for the habitability of a planet? The further question I'd like to pose is, does that affect the magnetic field? Is there a link between generation of a magnetic field, which we have, Mars and Venus don't have, and that which generates plate tectonics? I mean, I don't know the answer. I'm just wondering, because this whole plate tectonics revolution for me is a different way of looking at the Earth, and it has been extraordinarily successful. Thank you.
Thank you, Sue, very much. We've got time for questions, so do put your hand. We'll come around with a mic for those questions. We've got questions for Sue on this.
Thank you. Thank you very much indeed, Sue. A fascinating lecture, for especially at such short notice. It really brought home to me two things which you mentioned. The fitting together of the African European plate and the American plate and magnetism. Edmund Halley in the late 17th century hit upon both. In the voyage of HMS Paramore, 1697 to 1702, where he says at one stage, wouldn't it be as though somehow the two could be pushed together? And his studies of the geomagnetic field as far south as 52, where he again almost was overwhelmed. It was in a 60-foot ship, HMS Paramore, almost overwhelmed by a vast tidal wave, a bit like the monster you showed. And how he again mapped the magnetic drift, which is very similar to the continental field. And he was trying to use this, of course, hopefully for navigational purposes, for being able to fix the navigational positions more accurately for the Navy. But he was also working geophysically. And it's why I personally consider Halley as the first real geophysicist in what he was doing here. But yes, the parallels as well of Halley's early remarks are quite extraordinary. Thank you.
Well, thank you, Alan. Yes, I knew of Halley's overall maps, but I wasn't aware of his deeper interest in that, so thank you.
Any other questions for Sue? So can I ask a question? Did the advent of space photography have an impact on all this? Because actually knowing, sometimes when Google Maps came out, one could look at things and suddenly see, gosh, it's obvious how things are going together. But until then, you didn't have a really good, the same sort of picture, did you?
No, I mean, it is very visual, but the good fit actually comes not from coastlines, which are affected by things like river deltas and volcanic activity. It comes from taking perhaps the edge of the continental shelf. So you're mapping the continental rock, not what we just see above sea level. But yes, I think I could look at maps all day. Really, it's fascinating. But the space geodesy is the thing that made a huge difference. And looking at the geoid from the surface height of the ocean has been a very powerful technique.
Right, well, thank you. Oh, we've got one more. Thanks.
Mars and Venus, a lot of volcanism in the past, but still apparently no evidence of plate tectonics on those.
No, people are suggesting that there might be, but certainly not now. There's what has been suggested as stripes of magnetism in the Martian crust. And there are some suggested areas on Venus. If there is tectonics there, it's not tectonics like this established system we have on Earth, which people are modelling planetary interiors, actually, in much more varied ways. Now, people are thinking about the possibilities. In all exoplanet research, it's very tempting to be very human-centric, to be very Earth-centric, and to think that our planet is the only way planets can be. And it clearly isn't, because we've got Venus and Mars. And that goes right down to the core. One of the crucial things in producing a magnetic field is getting enough energy into the core. But it turns out there are ways you can produce a magnetic field without having a solid inner core and a liquid outer core. You can have iron snow forming at the top of the core. And people are sort of expanding the parameters of the planetary modelling. And one of the things they look at is whether you might have been able to return crustal rocks to the mantle through some sort of whole planetary overturn. You know, you get a stagnant lid and the heat's still churning there underneath it, and then, whoa, it all goes under. I don't know. Be exciting to find out, though, wouldn't it?
How about superrotation?
It seems like anything could happen in the core models at the moment, but they are only models.
We're going to have to just keep an eye on the time. We're just going to have to move on. Thank you, Sue, very, very much indeed. You'll see that we're not actually...